Our next lesson will be on parametric equations. An example of a parametric equation looks something like what you have over here. T is called our parameter, and for every value of t, it corresponds with a different x and a different y value. We'll go through some examples shortly. Take out your calculators, if you still have them. Change your mode. You want to be in parametric mode and not function mode. We're always in radian mode, but we want to be in parametric mode. Two things about parametric mode. Now, when you hit the X key, it doesn't come up as an X anymore. It comes up as a capital letter T. It in no way affects anything that you do with your calculator. And when you go to Y equals, it doesn't say Y equals anymore. It says X of T and it says Y of T. And we always have to put two different things in, one for X and one for Y. We'll be graphing as well. Actually, one last thing with your calculator. If you go to your window, there's an X min and an X max and a Y min and a Y max like you've had before. There's also something else. There's a T min and a T max and a T step. Normally our T min is 0 and our T max is 2 pi. Sometimes we have to change it, but that's pretty standard. The important part is your T step, and your T step should be about 0.13 with a bunch of other digits. Not really sure what they are. What that is at every interval, 0.13, 0.26, 0.39, it's substituting in values for T to get you the corresponding X and Y values. If your T step is too large, you get a very strange picture. If your T step is very small, it takes forever to graph. So keep it around 0.13 if you can, but we're going to change it up shortly. Okay, so let's try an example. So let's let X of T equal to sine of T and Y of T is equal to cosine of T. So go ahead, put that in your calculator and graph it and see what you come up with. We will also be taking derivatives. We'll do that shortly. When you graph it, you can hit pause if you like. You get circle. Perfect circle, centered at the origin, radius of 1. Okay, think about way back in your geometry days when you had to write an equation of a circle. Okay, centered at the origin, it looked something like this. X squared plus y squared is equal to your radius squared. Okay, if you substitute in this particular example sine of t in for x and cosine of t in for y, and you look at your calculator, your radius is equal to 1, what you have is this. Sine squared t plus cosine squared t is equal to 1. I just changed it from x and y to parametric. Okay, this should look familiar to you. That you've done before. That's called your Pythagorean identity. And this is an example of where it works. Okay, so let's stay with x of t and y of t. I will tell you, the only time I keep my calculator in parametric mode is if I want to do a graph. In any other case, I go back to function mode, because when you hit second calc with your calculator, if you're doing it in parametric mode, you have limited options. When you do second calc in function mode, you can find a point of intersection, you can find maxes, you can find mins, you can do all sorts of things. The choice is yours, but honestly, I only keep it in parametric mode if I want to see what my graph is looking like. Okay, so let's stick with the example that's up here. We can take first derivatives, we can take second derivatives, we can get tangent lines, we can do everything like we do in function mode. Just take note, I'm going to point to the y here. When you're taking the derivative of y, it's with respect to t, because t is your variable. When you're taking the derivative of x, you're doing it with respect to t as well. Okay, if we're looking for the slope of a tangent line, we're still doing dy dx. And in this example here, or in all examples, the way that we take the derivative of y with respect to x is first we take the derivative of y, but when we do that, we're doing it with respect to t. So it's dy dt, and the denominator right here, the derivative of x, again, we're with respect to t, so it will be dx dt. And this is your formula for taking the first derivative. Okay, working with this example here, what is your derivative? The derivative of y with respect to t. The derivative of cosine, you all know, is negative sine of t. And the derivative of x with respect to t is cosine of t. So this is what your first derivative is. If you want to say that it's negative tan t, that's absolutely fine. Okay, because it is. Taking the second derivative now is a little bit different. So let me actually just simplify this. And we said that this was negative tangent of t. Taking the second derivative, d squared y over dx squared, there's a little process going on here. We take the derivative of the derivative, so we take the derivative of negative tangent of t, and you get negative secant squared of t. And there's one more step. You now have to take the derivative of dx dt one more time. So that would be cosine of t, and if you want to simplify that, you get negative 1 over cosine cubed t, if I did that correctly, or you can make that negative secant cubed of t. The rule for the second derivative looks like this. D squared y over dx squared is you're taking the derivative with respect to x of dy dx. So that was my derivative of negative tan, wound up over here. And the new part is now my derivative of the denominator is dx dt. And that's just something that you have to memorize. Okay, we can look for horizontal tangents, we can look for vertical tangents, we can look for all kinds of things. So let me just get rid of this right here. And I want to just put some things back up. Okay, I want to put the original derivative that we had was negative sine of t over cosine of t. And the original graph was actually your unit circle, right here. So if I'm asking you for a horizontal tangent, you know that your slope is 0. The only way that a fraction can possibly be 0 is if your numerator is 0. So if we're looking for a horizontal tangent, we want this to be true. Negative sine of t is equal to 0. If we're working on the interval from 0 to 2 pi, we don't really need the negative sign. That's at 0, pi, and 2 pi. So t is equal to 0, pi, and 2 pi. I'm going to disregard 2 pi because 2 pi is the same as 0. So if I ask you for the point where we have a horizontal tangent, let's just try the 0 right here. If I put a 0 here, okay, my x-coordinate is now sine of 0, and sine of 0 is 0. So when t is equal to 0, my x-coordinate is 0, and when t is equal to 0, my y-coordinate is 1. And take a look at the graph here. When you go to the point 0, 1, and you draw a tangent line, you have a horizontal tangent. Okay, we could do the same thing with pi. And we would get down here our second horizontal tangent. Okay, let's try vertical tangents. Vertical tangent is when your slope is undefined, a fraction is undefined when the denominator is 0. So we're going to let cosine of t equal to 0, and t would be pi over 2 and 3 pi over 2. Okay, let's try to get our coordinating x and y points. Let's work with pi over 2. If I put pi over 2 here, sine of pi over 2 is 1. So my x coordinate is 1. If I put pi over 2 in place of y, cos of pi over 2 is 0, and I'm right here. And at the point 1, 0, we have a vertical tangent, and you can see that we do. Okay, so we can get concavity, we can get tangents, etc. Let's try one more example. I'll show you one other type of question that I can possibly ask. Okay, so let me give you an example. Let's let x equal t squared minus 2t, and let's let y be t squared. And that's on the interval from -3 to 3. And if you would like to graph that in your, well, don't graph it yet. Don't graph it yet. Hold on. So I can ask you a couple of different questions. I can ask you, what is the leftmost point? Or I can ask you the rightmost point. I'd be asking you the same question. So think about it. Left and right is your x-axis. So the leftmost point, we want to minimize x. We want to minimize x because we're going horizontal. So to find a max or min, you know exactly how to do it. X prime of t is equal to 2t minus 2. There's my derivative. Set it equal to 0, and our critical point is t is equal to 1. Okay, sign chart. We have ends, we have -3, we have +3, and we have the number 1 here. Okay, substituting values in, you would get a negative, you would get a positive. That's showing me that when t is equal to 1, you have a min point. Okay, so when our leftmost point, when t is equal to 1, I'm here, 1 minus 2, my x value is -1. My y value is 1, and we're going to graph that shortly. I'm going to leave that up there. Okay, so if you're looking for the leftmost point, you're going left and right. Left and right is your x-axis. If I ask you the highest point or the lowest point, that's our change in y. We're looking for dy, dt. So let's go with lowest point. So with the lowest point, we're working with our y-axis because our y-axis goes high and low. So dy dt is equal to 2t. And when you set that equal to 0, your critical point is 0. One more time, a sign chart, -3, 0, +3, and substituting values in, negative, positive, there we go. We have our min, we have our lowest point. So when x is 0 and we put a 0, when t is 0 and we put a 0 here, my x coordinate is 0 and my y coordinate is 0. Okay, what I would like you to do now is in your calculator, going into y equals, put these two in and see what your graph looks like. And you'll see that your leftmost point is right here. You'll see that your rightmost point is right there. Okay, and there's just one more thing that I need to show you. It's called arc length. You can calculate the length, the perimeter in parametric equation, very similar to what we did before. The length is, I'm going to say a to b. I think they have it in Greek symbols, but a to b works. And it's dx dt squared plus dy dt squared dt. Okay, these are your derivatives. I know you know how to do that. The most important part here are your bounds. The phrase that we use is traversed. We want the graph to be traversed exactly once. You graphed before sine of t and cosine of t. And your window, your t min was 0 and your t max was 2 pi. If you go back to that and you let your t max be 4 pi, you're going to get the same picture. if you look closely at your graph, you're actually going to see it being traced over. So we want these to be the smallest bounds where you get the entire picture. That's the trick to this. And that's it for parametric equations. In next video, we do something with vectors and parametric equations. We'll do that next time.